everybody, in this video we are going to implement the velocity of the wheels in Arduino code. Remember that it is a requirement for the controller. Due to the last video we calculate the time between ticks. We are going to join the concept in this video, trying to calculate the linear and angular speeds of the wheels. So let's get to it. Please like, share and subscribe to my videos. It helps me to make videos like this. In this video, we are going to find what is the velocity of the wheel, what is the speed of that wheel. There is a variable that we need in the controller. Then we have right here, I try to draw something like an encoder with only four holes and a code, a little code that try to summarize the last video that we watched in this channel. In that last video I try to find what is the velocity between ticks, and in that video we found three principal variables. Those variables are the muestreo anterior interrupción R, de muestreo actual de interrupción R y delta muestreo interrupción R. The first one, the muestreo actual de interrupción R, is the variable that is inside in the while loop, is the variable that is actualizing, is the current variable of the time, and the second one is the muestreo anterior de interrupción R, is the last tick time of is something like the last tick time that we have registered in our Arduino. And delta muestreo interrupción R is the difference between the current interruption, the current time, and the last time, the last tick that we register in our Arduino. And that difference is the delta, and that is the time that we found in the last video. In this part we have to decode the code. Look at that, in the while loop there is a variable that is the current time in our Arduino. That is the muestreo actual de interrupción R is saving the time between ticks. There is a time that is actualizing, and T1 is associated to the last interruption time. Remember that the loop is a cycle. In that cycle is saving, in every sample of time is saving the time that the Arduino has, and that variables that muestreo actual de interrupción R is saving that time when it's produced, when it happens an interruption, then that loop is broken, and we are going to execute the function, the interruption function. What is the interruption function? Remember, the loop is saving the current time, but when we execute the interruption, we generate the delta muestreo interrupción R, que es the difference between the times, the muestreo anterior de interrupción, muestreo actual, muestreo anterior. In this case, is the difference between the T2, that is the actual time, and the last time, that was the time that was recorded in the last interruption, that is T1, and delta is equal to T2 minus T1. And in muestreo anterior de interrupción R is save the time in this interruption, the actual time in this moment. In this moment, the current time is saving in that variable, because we are going to move, we are going to calculate the difference between tick and tick, and then we have to actualize this variable, and that's it. It's very easy. It's very easy to understand it. Okay, summarizing. At this time, we have the different, that is the time between ticks. We have that time. With that time, we have to calculate what is the velocity of the wheel, what is the speed of the wheel. Then we have that time. With that time, we could calculate some variables that those are very important. The first one is the angular velocity of the wheel. What is the angular velocity? In this case, the angular velocity between ticks is 90 degrees. That is we have only 4 holes, and in the holes are distributed between 90 degrees. That 90 degrees is divided by delta. And radians, we could call it P over 2 over delta. P over 2 is 90 degrees in radians. Over delta is the time required to move that grades, that part of the wheel. And we could change our expression. In this case, a wheel have 2p radians. Over 20, in my case, I have an encoder, a real encoder that has 20 ticks. But in this case, it's a particular case. My case, we have 20 ticks. 20 because I have this encoder, but you could have 100, 200, and then it is important to change that 20 for the number of ticks that you have. In this case, it's 2p over 20 and over delta. Because of that, the time, the expression is radian. The unities are radians over seconds. There is a velocity, and the linear velocity in this case is the linear velocity is a singular expression, is a expression that is the angular velocity by the radius of the wheel. It's important that is the radius of the wheel, not the radius of the encoder. In that drawing, I made that thing wrong. There is no the radian of the encoder, it's the radian of the wheel, the radius of the wheel. In this part, we could determine that the angular velocity is calculated with 2 parts. The first one is that we have a variable that is called frecuencia. That variable is 1 over the time delta. 1 over delta is the frequency of the wheel. That frequency of the wheel is 1 over the time between ticks. That is important that you understand it. Then if we have defined what is the frequency, we could calculate the angular velocity. The angular velocity is the frequency. You could see that if you multiply it, if you make the frequency by 2p over n. What is n? N is the number of ticks, the number of holes that your encoder has. That is very important. In my case, that n is 20. In your case, you could have 100 to 200 and a lot of more. I really don't know how many ticks are actual there is a common encoder has. Really, I don't know. And if I have the angular velocity, I could find the linear velocity multiplying, make it that multiplying between the angular velocity plus by the r. R is the radius, the length of the wheel. That is the radius of the wheel, and that is the linear velocity that we have, and that's it. It's really simple, and we could right now implement it in code, and that's it. The real implementation is too simple. Right here I have the code that I make to try to measure the velocity of the wheel. The first variables are the common variable that we use in the last videos, that is the muestreo actual de interrupción, muestreo anterior de interrupción y delta muestreo de interrupción R. Remember that R is the right wheel, and we could make it for the left wheel. I defined encoder R is the 3 pin and the llanta R is the 11 pin. Those are the pins that we are to connect the encoder and the llanta, that is the PWM signal of the bridge H. We have another variables that are double variable, that is frecuencia R, what is omega R, and B sub R, that is the angular velocity and linear velocity. And I defined an entire variable that is n is equal to 20. That is the number of pins. We have the interruption function, and the serial begin to try to debug our program. The function that is the R encoder, that is the interruption function, and I defined in this function the different lines that you watch in the last video that are the same lines, and other one that I explain later. And we have the while loop. Remember, please, I have this while loop. In this while loop we have firstly the actualizing variable, that is the muestreo interrupción, that time, that actual interruption, that actual time. We have a serial print trying to debug our program, trying to find that the variables are okay, and an analog write, that is something that we could handle our speed of our wheel, something like this. In this case we could have a 100 PWM. And remember, I only create the frequency variable. That frequency variable is equal to 100 over delta muestreo interrupción. That delta muestreo interrupción is the time between ticks. And why 1000 over delta muestreo interrupción? Because that delta muestreo interrupción is saved in milliseconds. Then we have to multiply that variable by 1000 to find that variable in seconds. So let's program our Arduino, and we are going to watch if that example helps and makes the thing that we try to make, something that we have to make. In that we open the serial plotter, and you could see that this variable that is make in this graph, this variable is the frequency of R. In this case the wheel is moving, is turning with a PWM of 100, and that makes us that we could change it. In this case we are going to change the PWM to 200, and we could see right now the wheel is moving faster, but we could find that the variable the frequency is higher in this moment. We have higher peaks, and we have lowers. We have a bigger signal. That is so important, and that is something that we have to ensure, and something that we have to try to improve, because we have a lot of noise is a noiser signal, but we have to improve it. That is something that we have to make it. In this part, I could create the WR, that is the angular velocity. In this case, WR is equal to 2 multiplied by P. In this case, I write the P number with 6 decimals, something like this. And 2P, that is multiplying by frequency. Remember that thing. That is multiplying is 2p over n. In this case, n is 20. And that expression is multiplying by frequency r. Is very, very important that you have to take in count that. And we have right now the omega r, that is the angular velocity of our wheel. The angular velocity of the wheel. That's it. I could save it. That frequency I'm going to change in the serial print, and I'm going to graph that velocity, the angular velocity. I save that program, and we are going to watch it, that variable, in our graph. So let's open the serial monitor, and we could see that the expression, that the movement of the signal is similar. We have changed the magnitude of the variable, but is the same result. It's very easy to have it the angular velocity of the wheel, and we could change the velocity, and it changes the magnitude of the variable, like this. I save it, and I open the monitor serial, and you could see that the graph is higher in this moment. The angular velocity is bigger in that moment. But remember, the real important variable is the velocity of the wheel, the linear velocity of the wheel. In this case, I have to define what is the radius of the wheel. In this case, I defined the diameter of the wheel, something like 6 over 8 centimeters. In this case, it defines a centimeter variable. And a centimeter variable, no, a centimeter parameter. And the linear velocity is equal to the angular velocity multiplied by the radius of the wheel. In this case, the radius of the wheel is that variable, is that parameter diameter over 2. And that's it. That is our linear velocity. That is the variable that we want to find in this video, and that is the really important variable if we have to control the velocity of the wheel, and we have, if our controller works according the specification. Those are so simple. Those are a really simple code. Only with 3 lines we could calculate the linear velocity of our wheel, and you could see it. In this moment we have that linear velocity, is that velocity that is plotting in our graph. And that's it. It's really easy to have it. and I really that you enjoyed this video, that you really like it. I changed in this part the PWM signal, and you could see that the wheel accelerates, then makes that the graphs moves something higher, and that's it. It's really simple to have it. I really that you enjoyed this video. Please like, share, and subscribe to my channel. It helps me to make videos like this, and I really enjoy to make it for us. And thank you very much. Bye bye, see you later.